What's up everybody and welcome to a new video. And in this video, we're going to go over my notes for mutability in Python. And here, I first want to cover some definitions. Namely, the first one states that objects whose value cannot change in place are called immutable. And examples for that are numbers, strings, boolean, none, and tuples. So now I want to go over an example with a tuple here to demonstrate what it means that an object is immutable, i.e. what it means that its value cannot change in place. So therefore, I've prepared here this tuple. So here we have a tuple with 1, 2, and 3, and I'm storing that in a variable a, and then here I'm printing out the ID of that variable. So now if you run this, then we get this ID. And now let's say that we want to add a 4 to this tuple here. So therefore then we could say a plus equals, and then we put here, or we add a tuple. So with this just one element, so the 4. And then let's also print that out. So here you can see now we have a tuple with 1, 2, 3, and 4. However, if I print out the ID again, then you can see that we actually get here a different ID than we had before. So what it means is that when we added here this 4, then actually a new tuple was created and we didn't change this original tuple here in place. And here I also have an illustration to visually explain what's going on here. So let's open this. So here what's happening is the following, namely when we say here a equals this tuple, then this tuple object is created, stored in a specific place in memory, and then a points at that place in memory. And in our case, this place had this ID here. And then when we add here this 4, what happens that a new tuple is created, stored in a different location in memory, and then a points at that new location. So that's why then we get here a different ID. So as you can see, when we try to add here this 4, actually a new tuple was created and this old one here wasn't changed in place. Okay, so that is here now the first definition here that I wanted to cover. Then the next definition states that objects whose value can change in place are called mutable. And examples for that are lists, dictionaries, and sets. So now let's look at an example with a list to show what it means that an object is mutable. So therefore I've prepared here this list. So here we have a list containing 1, 2, and 3, and we store that in a, and then printing out here the ID of a. So this time we get here this ID, and now let's add a 4 to this list. So here let's say a plus equals this list with a 4, and then let's also print this out. And then here, as you can see, now this list contains a 4. And now if I print out the ID, then you can see that this time actually we still have the same ID. So what it means is that when we add here this 4, we actually changed our original list here in place, and now the new one was created. And here I also have again an illustration to visually show what's going on. Namely, what's happening is the following. So when we say here a equals this list, then this list is created, stored in a specific location in memory, and then a points at that location. And in our case, we got here this ID. And then when we add here this 4, what happens is that we actually change this original list here in place and simply add the 4. So we are still using this location in memory, and a is still pointing at that location. So therefore then we still have here the same ID. So this is what happens when an object is mutable. And here, just as a side note, here in this case, you would obviously use the append method to append an element to a list. However, I used here this plus equal operator because I wanted to make this list example here more comparable to the tuples example. However, if I now here use the append method and then here run this cell again, and then here say a dot append a 4, then we also get the list that contains here the 4, and we also still have here the same IDs. Okay, so that is then the second definition that I want to cover. And with that, then we have covered all the definitions that I wanted to cover. So then let's get to the next note, which is about situations where mutability might cause a problem and how to deal with it. And here the first situation is about copying variables. So to demonstrate that, let's use again here this list. So here a equals this list containing 1, 2, and 3. And now let's copy this variable. So let's simply say b equals A. And now let's say that we want to change something about A. So let's here change this 1 into a 99. So therefore then it's simply say A brackets and then 0. And this should be equal to 99. And then let's print out here also A. So here then, as you can see, A has changed. So this first element is here, it's not a 1 anymore, but it's a 99. However, if I now print out B, then you can see that this has also been changed. So there's also now here this 99. So why is that? To show that, I've prepared here again an illustration. So let's have a look at that to see what's going on. So here, what's happening is the following. So when we say A equals this list, then the list is created and stored in a specific place in memory. And then A points at that place in memory. And then when we say here B equals A, then what this means is that B should simply point at whatever A is pointing at. So it's also pointing at the same place here in memory. And we can also verify that by printing out the IDs here. So we say print ID A, and then also print ID of B. Then you can see that we get here the same ID. So therefore then, when we change something about A, because B is still pointing at that same place here in memory, B is also changing. And depending on your use case, this might not be what you want. So in order to solve this problem, what you have to do is then use here this copy method. So here then, instead of saying B equals A, you say B equals A dot copy. And now if I run this here again, then you can see we get here different IDs. So then when we change something about A, then A still changes. However, B is now still the same. So this still contains 1, 2, and 3. So here again, to show that what happens is namely the following here. When we say A.copy, then a copy of this list here is created and then stored in a different place in memory. And then B simply points at that different place. So therefore then, when we change here something about A, then this doesn't affect here B. Okay, so that is then the first situation here that I wanted to cover. However, here I also have a side note, namely this states that a copy can also be created with slice notation. So here, instead of using here this copy method, what you also can do is to say here, or create a slice where you don't use or don't specify the start and the end. So now if I here run this again, then you can see we get here different IDs, and therefore then B again here is not affected. Okay, so that's the side note that I wanted to cover. Then the next situation where mutability might cause a problem is when passing a mutable object to a function. So to show that, I've prepared here this code snippet. So here I'm creating this variable called numbers, which is simply again a list containing 1, 2, and 3. And then here I'm defining this function, which is called append, which takes in a list and then simply appends a 4 to that list. And then here it returns that list. So now let's use this function here to create a new numbers list. So let's say here then numbers underscore new. And here then we call the function and set the parameter, the list parameter equal to our numbers variable. And then let's also print out those numbers new. So then if I run this, then you can see we get here this list containing 1, 2, 3, and 4. So nothing unexpected. However, if I now run here numbers, or if you look what numbers looks like, then we can see this has also changed. So this now here also contains the 4. So again, to show what's going on, I've prepared here this illustration. So let's have a look at that. So here, what's going on is the following. So here we say numbers equals this list. So in that case, then this list is created and stored in a specific place in memory. And then numbers points at that specific place in memory. And then when we here call this function and say here on set the list parameter equal to numbers, what this means is that list should point at whatever numbers is pointing at. So it's also then here pointing at the same place in memory. And we can verify that again by printing out the IDs. So if I say here then print ID of numbers, and then here in the function, let's also print out the ID of this list parameter. And then here, if I run this again, then you can see that we have here the same IDs. So therefore then, when we here append the 4 to our list variable within this function, because numbers is still pointing at the same place in memory, because of that, then it is also affected. And again, depending on your use case, this might not be what you want. So to solve this problem, or to get around this problem, what you can do is again use simply this copy method. So here, when we call the function and set the list parameter equal to this numbers function, here instead of saying list equals number, we can say list equals numbers dot copy. And then if I run this here again, then you can see that we get here different IDs now, and therefore then here numbers is not affected. So if you look here at our illustration again, what happens is when we say here list equals numbers.copy is that we create a copy of this list here, and this copy is then stored in a different location in memory, and list then points simply at that different location. So therefore then when we here then append this 4 to our list, this then doesn't affect our numbers variable, and therefore it is still unchanged. So that is one way of getting around this problem. Another way that you could do is simply use this copy method here within this function definition. So for example, if I delete this here again, and then here simply create a copy of our list. So if I say list equals list.copy, and then here run this again, then you can see again that we get here different IDs. So therefore numbers is then again not affected. Okay, so that is then the second situation that I wanted to show where mutability might cause a problem. And here I also have a side note, and this is about in place versus not in place functions. Namely, not in place functions return an output, and one has to manually store that into a variable. So to show what I mean by that, I've prepared here this list. So this contains the numbers 3, 1, and 2. And now if I use this built-in function sorted and pass in our list here, then we get here a sorted list. So this function here returns an output. However, if we look at our original list here, then we can see that this has not been changed. So this is another in-place function, and then here in-place functions don't return an output and automatically update the respective variable. So to show that, we can use here, for example, this sort method. So then if we simply run that, then you can see that we don't get here an output. However, if you look at our variable, then we can see that now it has actually been changed. Okay, so that is now the side note here that I wanted to cover. Then the next situation where mutability might cause problems is with default values in function definitions. So to demonstrate what I mean by that, I've prepared here this function. So here I'm setting this parameter equal to this default value, which is an empty list. Then we append a 4 to that list and then simply return that. So now let's call this function. So if I run this, then here you can see we get a list with a 4. So nothing unexpected. However, if I now run this function again, then we get here actually a list with 2 4s. And if I run it another time, then we get here a list with 3 4s. So now to understand what's going on, you have to know one thing first, namely these default values here, they are evaluated at the function definition and not when the function is called. And I will explain that in more detail in another video. So if you're interested in that, I will put a link to that video into the video description. But now, just to show that that's actually the case, let me here then run this cell again. And now to access those default values, what you can do is to say append and then underscore underscore, and then here you can use this defaults attribute. So now if I run this, then we get here the tuple with all the default values. So in this case, it's just this one. So let's access that by saying brackets 0. So now we have here this default value. And now let me go here over this illustration to show what's going on here with the mutability. So let's open this. So here what's happening is the following, namely when we are running the cell here with the function definition, then the default value is already created. So this empty list here is created in memory and then stored in a specific location. And then the default value variable here simply points at that location in memory. And then when we call here this append function, what happens is that we set this list parameter here equal to the default value. So this list parameter is simply pointing at whatever this default value variable here is pointing at. So it's pointing here at the same location in memory. And we can verify that by, again, printing out the IDs. So let's say here print ID of the list. And then here, let's also print out the ID of this default value variable. So let's say here then print ID of this default value variable, and let's also put in here a print statement because we need that. We're going to need that in a moment. So now if I run this here again, then we get here this specific ID. And now if I run here this, or if I call this append function, then you can see that we get here the same ID for our list parameter. So what then happens is when we here append a 4 to our list, is that because this default value variable is still pointing at the same place in memory, it is also going to be affected. And we can show that here by printing it out. So here we ran, or we call this function, and then afterwards, if we now print out here this default value, then you can see that it now also contains a 4. And again, if I run here this function again, then now we have these two 4s. And if I print out, if I print out here this default value again, then you can also see that we have now here two 4s. So now to get around this problem, what you have to do is here the following. Namely, instead of using here a mutable object, what you say for this default value is simply list equals none. And then within the function, what you then do is to say if list is none, then only then you're going to create that empty list. So in this case, then we create here, we set the list equal here to this empty list. So now if I run this, then you can see that now the default value here is none and it has this specific ID. Then if I call here the function, then you can see that this list parameter has a different ID than our default value. And here our list only contains this 1 4. So then if we look again at our default value, this is still this none value. And then here, if I call the function again, then you can see that this time we again have another ID. So a new list here was created, and therefore then our list still only contains 1 4. And if we again look here at this default value, then here you can see it is still none. So now here, if you look at again at our illustration, what's happening is that here, when we run the function definition, then what's happening is that we create here this none value. So this then stored in a specific place in memory, and then our default value variable points at that. Then when we call the function, then our list parameter is then set equal to a specific list. So this list here is then created, stored in a different location in memory, and then the list variable points at that. So therefore then, when we append a 4 to our list, then this doesn't affect our default value. Okay, so this is then the third situation where mutability might cause problems. And then the last situation that I want to cover where mutability might cause a problem is when changing a mutable object while looping over it. And here I want to cover 3 examples. So let's start here with a list. So therefore I've prepared here this list. So here we have a list of numbers going from -5 to 5. And now let's say that we want to remove here those negative numbers. So therefore we can loop over this list. So we can say for number in numbers. Then we check if the respective number is negative. So we say if number is smaller than 0. And if that's the case, then we want to remove it. So then we're going to say numbers.remove. And then here we want to remove the number. And then let's also print out this list. So now if I run this, then you can see we get a strange behavior here where we have only removed every second negative number. So we have removed here -5, -3 and -1. However, -4 and -2 are still in the list. So now to get around this problem, what you have to do here is in this for loop, instead of looping over this list here, you simply loop over a copy of this list. So therefore, let me here copy and paste this cell. And then here now, if I say dot copy and then run the cell, then you can see that we have removed here all the negative numbers from our numbers list here. So that's the first example that I wanted to show. Then the next example that I want to show is for dictionaries. So here I have prepared this dictionary. So this contains information about users. So user 1 is active, user 2 is inactive, and user 3 is also inactive. And now let's say that we want to remove these inactive users here. So therefore, let's loop over this dictionary. So we're going to say for user, comma, status in users.items. And then here in each iteration, we want to check if the user is inactive. So we're going to say if status equals inactive. Then we want to remove that specific user. So we're going to say users.pop and then pop the user. So now if I try to run this, then you can see that we get here a runtime error. And that's because the dictionary changed size during iteration. And here, if I also print out this dictionary, then you can see that user 2 here was actually removed. However, user 3 is still in that dictionary. And here again, to get around this problem, what you have to do here is in this for loop, instead of looping here over our dictionary, you simply loop over a copy of that dictionary. So here then you simply say again dot copy. And now if I run it like this, then we don't get an error. And if I print out here the users, then you can see that the inactive users have been removed. So that's the second example that I wanted to cover. And then the last example that I wanted to cover is for sets. So here I've prepared this set here, where we again have the numbers -5 to 5. So let's again try to remove here those negative numbers. So we're going to say for number in numbers, and then we check if the number is negative. So if it is smaller than 0, and if it is, then we want to remove it. So we're going to say numbers.remove, and we want to remove the number. So now let's try to run this. And here, as you can see, we again get a runtime error because the set changed size during the iteration. And if you look at here at the numbers, then you can see that in this case here, for whatever reason, here this -2 was removed, whereas those others are still in our set here. So again, now to get around this problem, you simply have to loop over the copy here. So if I make this here dot copy and then run it again, then we don't get an error. And then if I print out here the numbers, then you can see that the negative numbers have been removed. Okay, so those are the 3 examples that I wanted to cover with respect to changing a mutable object while looping over it. And with that, now we've covered here all the situations that I wanted to cover where mutability might cause a problem. So now let's go over the side note here, which is about nesting. Namely, when using nesting, a shallow copy might not be enough. And depending on the use case, you might need to make a deep copy. And to show what I mean by that, I want to cover those 4 situations here. So let's start with the first one here, which is the no copy situation. So therefore, I've prepared this nested list here. So this list contains 3 elements, and this first element is another list, which contains then the 1, and then here we have the 2 and the 3. So now let's copy this variable. So let's say here b equals a. And now let's make a change about a. So let's change here this first element. So therefore, let's say here a brackets 0, and let's set this to 99. And now here, let's print out also a. So here then we can see that this first element now has changed. So it's 99 and not this list anymore. And if we look here at b, then we can see that this has also changed. So here we also have this 99. And this is something that we already know, so we expect that to happen. However, I nonetheless want to show here this illustration that I've prepared. And that's because all the previous illustrations that we've seen so far are not entirely precise. Namely, what happens here when we create a list is then that this list is created and stored in a specific place in memory. However, that list actually doesn't contain the values within the list. So it doesn't contain here this inner list and this 2 and this 3. Instead, it contains here pointers to other locations. So for example, here, this element 2 points at this location, which in turn contains the 2. This element 3 points at this location, which contains the 3. And here this element 1 contains another location, which contains this inner list here, which in turn contains another pointer, which then points to this location, which contains the 1. And we can verify that by printing out the IDs of all of these elements here. So therefore, let's run here the cell again. And then here, let's say print ID of A. Then we're going to print the ID of this first element, so this inner list. So therefore, you say 8 brackets. Then we're also going to print out the ID of this 1, so the element within this inner list. So therefore, we say here brackets 0 and then another bracket 0. And then let's also print out the IDs of the 2 and the 3 here. So therefore, we use then here index 1 and index 2. And now, if I execute the cell here, then you can see that all of these elements here have different IDs. Okay, so now that we know that all of these elements here are stored in different locations, let's continue with our code here. So then here, next we say B equals A. So this simply means that B should point at whatever A is pointing at. So it's pointing also here at this location. And again, we can verify that simply by printing out also the ID of B. So here then we can see that those IDs here are the same. So then next, when we say here, when we change here this first element of A, what happens is that this 99 is created and stored in a specific location in memory. And then here this first element of this list in A here is not pointing here at this inner list anymore. Instead it is pointing at this 99. And since B is still pointing at this location, it then also changes, which we have seen here. So that is the first situation here that I wanted to cover, namely this no copy situation. Then the next situation is a shallow copy plus changing the elements of the outer list. So to show that, let's again use here our nested list. And then let's copy here a variable A. So we say B equals A, but this time we say that it equals A dot copy. So then let's again here change the first element and let's set it to 99 and then print out A. So here again it changes, and now if you print out B, here you can see that it has not been affected. So this is also something that we already know. However, again, I want to show here this more precise illustration. So let's open here this file. And then now let's go through it. Namely, what happens here when we say A equals this list, then again, this list here is then created and stored in a specific place in memory. And then all those values within the list are stored in those different locations. Then next, when we say here B equals the copy of A, what happens is that we create a copy of this list, which is then stored in another location in memory. So A and B are pointing then at different locations. And again, we can show that by printing out the IDs. So if I run the cell again and then say here print ID of A and then also print ID of B, then we can see those are different IDs. However, the elements within those lists, they are actually pointing at the same locations here. So for example, the first element of A points at this location, and the first element of B also points at that location. And we can also verify that by printing out here the IDs. So here, let's say A brackets 0, and then also here B brackets 0. So here you can see that those IDs are actually the same. So then lastly, when we here change the element of the first element of list A to 99. Then this 99 here is created and stored in a specific location in memory. And then the first element of A is pointing at that new location, whereas the first element of B is still pointing at this location where this inner list is stored. And A and B are still pointing at those two locations here. So we can also verify that. So let's run here the cell again and then print out here the IDs of A and B. So here you can see that those are still the same as before. So nothing has changed here. And now let's also print out here the IDs of those first elements of those lists. And here you can see that the first element of list B still points at the same location. However, the first element of A now points at a different location. So it's not pointing at this location anymore, but at a different location, which is then this 99. So this is why then our B here is not affected. Okay, so this is then here the second situation that I wanted to cover. Then the next situation is a shallow copy plus changing the elements of the nested list, so the elements of the inner list. So therefore, let's again here use our nested list. So here we store our nested list in A and then say B equals a copy of A. And now instead of changing this element here or this inner list here, let's change the element within this inner list. So therefore then we say here A brackets 0 to get the inner list. And then we say bracket 0 again to get to the 1. And then we set this equal to 99. Then let's also print out A. So here then you can see that now this 1 here has been changed to a 99. However, if I now print out here B, then you can see that B has again been affected. And that's even though we've created here a copy. So now let's see why that is. And therefore, let's again here look at the illustrations. So let's open this here. So again, what's happening is first when we create here this variable, this list here and store it in A, what happens is that this list here is created, stored in a specific place in memory, and then A points at that, and then the values within that list are stored in those different locations. Then next, when we say B equals a copy of A, what happens is that we create a copy of this list here, which is then stored in a different place in location, and then B points at that different place. So A and B are pointing at different locations here, and we can verify that by here running the cell again and then printing out those respective IDs. So let's print out the ID of A and then also B. So here you can see we have different IDs. However, the elements within those lists, they are pointing at the same locations here again. So for example, the first element of A points at this location and the first element of B also points at that location. So let's verify that by printing out the respective IDs. So here we're going to print out the ID of A bracket 0 and then here B bracket 0. So here you can see that we have the same IDs. And then lastly, because those two elements here are pointing at the same location here, then the ID for this inner element, so for this 1 here, is also going to be the same for A. It's also going to be the same for A and B. So again, let's verify that by printing out the respective IDs. So here we say then A bracket 0 and then B brackets 0 0. So here you can see that we have now also here the same IDs. So then lastly, when we run this cell, what happens is the following, namely this 99 is created, stored in a specific place in memory, and then here this first element of this inner list is going to point at that new 99. And since the first element in B is also still pointing at this location, because of that then our B here changes. And let's now verify that again by using or by printing out the respective IDs. So let's start here again with A and B to see that those have not changed. So here let's paste this and then run this again. So here you can see that those IDs here are still the same. So next, let's look at the IDs of those first elements here in A and B. if they are also still the same. So therefore, let's copy this cell and then paste it here and then run it again. So here you can see again, we have the same IDs. And now let's lastly print out here again the IDs of the first element of this inner list. So let's copy this cell and paste it. And then here you can see that this ID here has changed. However, both here for A and B, they are still pointing at the same location in memory. Okay, so this is now the third situation, namely when we use a shallow copy plus changing the elements of the nested list. And then the last situation is with a deep copy. So to demonstrate that, let's again use here our nested list. So here we store our nested list in A, and then here we say B equals a copy of A. However, this time we're not going to create a shallow copy, but instead we're going to create a deep copy. So therefore we need to import the copy module. So let's say here import copy. And then here we say copy dot deep copy. And then we want to have a deep copy of A. So then again, let's change here the 1 within this A. So let's say here A brackets 0 and then brackets 0. And let's set that equal to 99 and then print out A. So here, as you can see, we again have this 99 instead of the 1. And now, however, if I print out B again, then you can see that this time it has not been affected. So now let's look again at the illustration to understand what's going on here. So let's open this file. And then here, what's happening is the following, namely when we say A equals this list, then again, this list is created, stored in a specific place in memory. Then A points at that place in memory, and the values within those lists, within that list are stored then here in those different locations. Then next, when we say, or when we create here a deep copy of A, what happens is that we create a copy of this outer list, which is then stored in a different place in memory, and B points at that. However, with this deep copy method or function, we also create then a copy of this inner list here. And this is then also stored in a different place in memory. So then the first element of B simply points at that newly created list. And then here, as you can see, both of these inner lists of A and B are then pointing at the same value here, which is then 1. And we can verify that, all of that, by printing out the respective IDs. So therefore, let's run here the cell again. And then let's first print out the IDs of A and B. So let's say here print ID of A and then also of B. So here you can see there are different IDs. So they are pointing at 2 different locations. Now let's print out the IDs of the first elements here of A and B. So therefore let's copy and paste the cell here. And here we say A brackets 0 and then A brackets B brackets 0. And then here you can also see we have here different IDs. And then now lastly, let's see where here the elements of these inner lists are pointing at, if they have the same ID. So therefore here then we're going to say A brackets 0, then brackets 0, and B brackets 0 brackets 0. And then here you can see that we have the same IDs. Okay, so now then lastly, when we then change here this element of A, or of this inner list of A, what then happens is then that this 99 gets created and then stored in a different place in memory. And then here, this element of list A, of this inner list of A, is not pointing here at this 1 anymore, but instead it's pointing then at the 99. And this doesn't affect here this inner list of B. So that's why here B is not affected. So again, let's verify all of that by printing out the respective IDs. So let's start here with A and B again. So if I copy and paste this, then you can see that those have not changed here. So those IDs here are still the same. Then next, let's look at the IDs of the first elements of this list. So here, let's print them out again. And here we can see that they are also still the same. So as we can see, nothing has been affected here. But now if we print out the IDs of those elements of the inner lists, then here you can see that the ID of B, this is still the same. However, the ID of this inner list of A, this has now changed because it's now pointing at this 99. Okay, so this is now here why our B is not affected when we use a deep copy. Okay, so with that now, we've covered here all of these different situations. And this is why a shallow copy might not be enough when using nesting, and why you might need to make a deep copy. And then the next note states that even though tuples are an immutable type, their elements can actually be mutable. So to demonstrate that, I've prepared here this tuple. So here within this tuple, the first element here is a list which contains, and then here this one. And then here we simply B equals A. So now let's try to first change here this first element of this tuple, so this list here. So therefore then we say A brackets 0. And then let's try to set that equal to 99. And now if I run this cell here, then you can see that we get a type error because tuple object does not support item assignment, i.e. it's an immutable type as we have seen earlier. So now let's try here to change here this 1 within the list. So therefore then here we say A brackets 0 and then brackets 0. And then let's print out the A. So here now you can see that this 1 has actually been changed. And now here, however, if I print out the B, then you can see that the B again has been affected. So now to get around this, we again have to make a deep copy because we are using here this nested data structure and we've changed the element here of this inner list. So therefore, let's import here the copy module. So let's say import copy. And then here we say copy dot deep copy, and we want to have a deep copy of A. So now if I run this again, then we've changed here this 1 into a 99. However, if I run this cell again, then you can see that B has this time not been affected. And here, just as a side note, here I've also provided illustrations that show what's going on here in more detail. So you can have a look at those if you are interested. Okay, so now with that, we've covered here all the notes with respect to nesting and mutability. And with that, then we've covered all my notes that I wanted to cover with respect to mutability. So we've reached the end of this video. And then in the next video, we're going to go over my notes for comprehensions in Python. So thanks for watching, and hopefully I will see you in the next video.